Enough about why Bayesians and frequentists have different philosophy. Let's talk about how it actually works. Some of the notation looks pretty similar. We still have n as our sample size, y is what we're trying to predict, and the x's help us make those predictions. These parameters, theta, they have probability. And the prior says, here's probability based off, it might be opinion, it might be previous studies. We'll talk about different places where you can get a prior from. This is what the data says about that theta. It's based off the likelihood, and you put the information from the prior with the data, and what you get out is a posterior. That's what you give to the client. That's where you can actually make decisions about the population based off the parameters. The could be from previous papers or expert opinion, or it just works out nice so that we can use the Bayesian philosophy. And sometimes you can use other data or previous data that you got, which means you can stream data. Like we got n data points so far, and we create a prior based on that. And as we get new data, we add that in with a likelihood, and we get out a posterior distribution that has both of it all together. Now, there are some non-informative priors where you're like, I don't have any opinion or knowledge, but I still want to put on a prior to get the Bayesian philosophy. That's what the point would be. Or you could have junk priors or priors that give you the answer you want. So there is some abuse that could happen with getting the prior. Let me show you what it looks like with a picture. Here's our prior. Okay, this distribution is like sand, and our data is a different sand pile. This prior is very low. It's non-informative. It's not doing much. So there's only a little bit of blue prior sand going on top of our red data sand. And so this allows us to still use Bayesian terminology and philosophy, but not really overwrite what the data is telling us. I like talking about confidence intervals as 95% probability of capturing the parameter, but I don't really know what prior to put on it, so I use this non-informative prior. This is the way that you would envision it should work. There's prior and there's data. They're both kind of strong. When you lump them together, you get up with something that's not quite the prior, but also not quite the data. It's somewhere in between. And this is kind of the ideal. My prior expert knowledge helps fix the fact that the data wasn't quite showing things the way it should have been, but my data also helps adjust that my prior wasn't spot on either. The next example, of course, is where the prior is really strong and the data is weak. Maybe there wasn't a lot of data, or maybe there were some errors. And what do we get? We get a posterior distribution that is mostly the prior, slightly adjusted for the data. Of course, if the prior is wrong, you can see how dangerous this would be. In fact, let's do an example where the data is super non-informative and the prior is super strong. We basically get the posterior, which was from the prior, maybe this is like expert knowledge, and that overwrites anything the data has to say. So of course this could be abused. You have to be careful the way you're streaming in data. If the previous data is very strong and the incoming data is very small, all you get is reinforcing the previous data. That's not to say it should never be done. Like I've told the story of Dr. Tolley, who worked at Los Alamos, and that's, the government facility where they work with some top secret stuff and weapons and whatever. And they brought him a number, a single number, and said, we want you to do statistics. And he's like, how am I supposed to do statistics with a number? And they're like, one of our men died to get that number out of Russia. You will do statistics. Well, what do you think he did? I mean, this was 60 years ago. He, of course, made himself a prior and talked with experts and people who thought they understood what was happening in Russian. I don't know the details of exactly what the number was, but his data was super small and he got out a model, and that's the best you can do with only one number. So there are times when this might be appropriate. Here is the way the math looks. The posterior distribution is a combination of the prior times the posterior and divided by some constant that makes it come out nicely so that you have probabilities, because like all the probabilities have to add up to 1, rules like that. If you take a Bayesian class, you'll find they spend time. Personal opinion, like maybe too much time focused on how to pick a prior that works out really well mathematically with the likelihood so that you end up with nice, easy ways to calculate this value down here. Because this needs to be a function of the data, so this is going to have y values in it. It has to be the exact right form in order to make all the probabilities add up to 1 the way you want, and always be positive, stuff like that. So you can spend a lot of time on that. Most people in real life, when they start digging into a lot of complex Bayesian stuff, look, just tell me the prior it ought to be, and then I'm going to have some tricks to try to find this guy, which ends up being the very tricky, complicated part. What are some tricks? There's numerical methods. Some of them use asymptotic results to make them a little simpler, and importance sampling, rejection sampling, and the MCMC, which is super famous. If you've ever had Bayesian in a class, they'll talk about doing this MCMC. The idea is bouncing around in the probability set so that you can tell where the probabilities are, and then you can take all the probabilities, calculate them without fixing that little denominator piece, and they'll add up to something weird like 500, and so then you can divide everything by 500 so that it adds up to 1, something along those lines. Often a posterior distribution is way too complicated to try to integrate it out, but if you can bounce around, kind of like in the calculus class, right, you chop things up into rectangles and then add up the rectangles. Well, what if we just had a ball bounce around inside so that it could tell us how much area there was underneath? So here we have notation for working with that posterior, and you can find predictions, you can do hypothesis testing, and you can do confidence intervals, except it gets frustrating if you're a frequentist or Bayesian and people throw around the word like confidence and you're not sure what they're talking about. So Bayesians have changed to call them credible intervals instead of confidence intervals. And that way everyone understands which philosophy you're following. Credible intervals really do say 95% probability, where a frequentist would be like, oh no, that's not the right way to talk about it. So what do you get as good things from using Bayesian philosophies? The natural way, like I want to talk about p-value as being a probability that the parameter was the value. And frequentists would say, no, it either is or it isn't, 0 or 1. That p-value is actually the probability of the data under the model. And patients are like, what? Just use this in a way that would make more sense to be interpretable. The price you're going to pay to do that, though, is it's a little bit harder to not use the asymptotic methods and these plug-in values, and it's computationally very difficult. Simulations often help you do this, which 30 years ago, not even an option. Thanks to computers today, Bayesian stuff can actually be done, and there's been some great programming to help it. Also, you got to be careful about the prior. You do a bad prior, you're going to get bad results. So that MCMC, see this ball randomly bouncing around? In other words, we calculate probabilities and how likely it is to be here or there. What shape do you see? Oh, kind of looks like a bell curve. And so, as we use MCMC, we can see, oh, this is normally distributed. There is a possible flaw. Imagine if this ball had started way, way out in the tails. What would happen as it bounces around? It would come bouncing into where there's higher probability, but until it gets here to the normal distribution, it would look sort of like a uniformly flat distribution, because that's what the distribution looks like out there. So you would have to wait until the ball finally gets to where there's high probabilities to see it bouncing around in here. As such, there are some things that could be dangerous. That was a two-dimensional picture. Here's a three-dimensional picture, right, where instead of a bell curve, we have bell mountains. And if the ball starts here in a valley and it takes a while to get to a mountain, you're not going to understand the true appearance of this probability map that we're trying to map out. And if there's separate mountains, then this MCMC algorithm could get trapped within one highly probable group and not see that there are other highly probable groups. In other words, if you have multiple x's that you're trying to predict y, and a combination of those x's, x1 is high and x2 is high, is a scenario that's very likely. And maybe x1 being low and x2 being low is also very likely, but x1 and x2 being somewhere in the middle is not very likely. The MCMC algorithm will find one of them, maybe the x1, x2 being high, and it will say, oh, there's a lot of probability here, but it never traveled over to where x1 and x2 were low to understand that there's a lot of probability there. So you're not getting a full map of where the probability distribution is located. So when you're looking at the parameters, how does x1 help me predict y? It'll say, oh, it's always going to be high with x2 being high, and that leads to high probability. No, there was another scenario that you didn't find. Fortunately, these kinds of scenarios with this bizarre map with lots of probability mountains that are all separated, that's actually pretty rare. That doesn't happen very often. So this problem can be solved if you're careful in watching, and the bizarre things that you wouldn't know to watch for don't typically happen in real life. What things can we look for? Here's some terms. I'll show you some pictures that explain it better, but burn-in says wait until it's bouncing around in a good area. Make sure that it is bouncing around well and that there's not some area that appears to be missing out on. And thinning says maybe not take every single bounce. I'll show you why in a second. Here's a plot where the MCMC is trying to figure out where is the probability distribution for this parameter or this theta, and it started with a value for that was way too high. And it finally drops down low here, and then it starts bouncing around. And as you, a data scientist, looks at this, you're like, here's my burn-in. This is what it took until I converged to a nice probability space for this parameter. I know what you're saying. How hard was it to figure out that you're supposed to be down in that lower range? If this is an 8-dimensional model and all those variables have interactions, it might not be that easy to figure out where the right values are supposed to be. So you'd be looking at several of these plots and saying, I need to burn the first 200 MCMC iterations, and then I'm bouncing around in the probability space. Now, if you only have a few, you might see how, it's bouncing from here to here, but you have 100 dots in the way. You might say, let's only take every 10th dot. That's called thinning. It's an attempt to try to get a more unbiased view of where this probability space is. If your iterations are huge, like 10 million, you might not need thinning because it's going to bounce around well all the different places where it's supposed to be in that probability space. Here's what it actually looks like to do Bayesian analysis. This is real output from someone who's doing things, and the autocorrelation here, they're looking to see whether they need some thinning, and they've got posterior distributions. It looks like beta 1 has a nice rounded bell curve, and that's cool. Beta 2, though, has sort of this bimodal hump, so the value of beta 2 might be high or low, but in between is unlikely. The higher one has a little bit more probability. Okay, that's interesting. Now we can talk about how does this variable help us to predict y, this much effect, maybe that much effect. Beta 3 has a nice rounded curve, and now that you have the probability, the posterior probabilities for the parameters, you can go ahead and talk about the variable that you're interested in or whatever predictions you want to make. This is used in real life. Here is an example where a plane went down. It was in water, and they said they used Bayesian inference. I tried to look up exactly what it was, but I couldn't find the actual models. My guess is they had pilots saying, these are areas where it's more likely or less likely, or this is what the pilot was likely to have done, combined with information that they were able to get from the plane as it was going down, or things said on radio, flight plan, that sort of stuff. Put it all together, and they were able to locate where that plane was. All right, this video is already way too long. I appreciate your patience. I recognize that, but let's do a checkup on where you are in your project. Have an idea, define a goal, find the data. This should already be done. If you don't have data, it does mean you're behind and it's time to buckle down and make a decision, get some data. If you're at the phase where you're looking at your data and getting it in a program and fixing errors, you're a little behind, not too bad. I'm expecting most people to be where you're getting plots and response and trying to examine things and create a model. That's sort of the phase that we want to be at. If you're kind of validating and finalizing and you feel like your model's done, you're almost ready to start writing, you might be just a little bit ahead, not a whole lot. Writing the report, well, for me, that was always the hard part. Everybody has some section that's hard. Maybe it's getting the data or cleaning the data or doing the statistics or writing the report. Whatever it is, there's going to be some piece of this you don't like. That's okay. We can work through it. Notice write the introductions like last. I always write an introduction at the beginning and then delete it because later I look at it and I'm like, ugh, that was not the introduction I wanted. finalizing report, plan presentation, and making the presentation and upload it all and throw a party and cake is a lie. So tell us on the discussion board what step you're on, and we'll see a distribution of where people are. If you're running a little bit behind, you can say, oh, okay, I need to step it up. Or if you're ahead, you can be like, oh, good, that makes me feel good. Just tell us where you're at.